I'm Steve Butler, Vice President of Engineering for VPT. In this video, we will talk about the turn-on characteristics of our isolated DC-to-DC converters. We will demonstrate the DVHF2805S, a 5-volt single output converter. We will cover the undervoltage lockout circuit, its operation, the output soft start circuit, its operation, and turn-on delay times, and several different source and load characteristics. First, we will look at the DVHF undervoltage lockout protection function. So the input voltage is shown on this meter here and on the scope with a yellow trace. The output voltage is shown on this meter and on the scope with a blue trace. So first, we will slowly increase the input voltage, shown in yellow on the scope. When the input voltage reaches approximately 13.8 volts, the output will come on. So this is the undervoltage lockout feature. The converter will not come on until the output reaches the proper voltage. The undervoltage lockout has approximately 1 volt of hysteresis. As we slowly decrease the input voltage, when it gets down to about 12.8 volts, the output will turn off. Now, the input voltage can remain in this low voltage condition, for example 10 volts, indefinitely without any damage or malfunction to the converter. Okay. Next, we'll look at the output voltage rise waveform. And first, we will use a slowly rising input voltage. So I'm slowly turning the power supply up, and we'll watch the oscilloscope. We can see when the input voltage reaches 13.8 volts. In the yellow trace, you can see it's a very slow rise, but we have a very smooth and well-controlled output voltage waveform shown in blue. Next, we'll adjust the input voltage to 28 volts, and we will take the input voltage soft start waveform with a very fast input rise time. So again, in yellow, you can see the input voltage comes up very fast, and again, the blue waveform shows the output soft start functioning normally. Next, we can look on the oscilloscope, and we can measure the turn-on delay time. So we measure from the application of input voltage to the 90% point on the output voltage waveform, shown here. And we can see the turn-on delay time for this particular converter is 11 milliseconds. Now, not specified on our data sheet, but sometimes also measured, is the output voltage rise time, usually measured from 10% to 90% on the output. On this particular waveform, it's 7 milliseconds. Now we'll take a look at the output voltage rise waveform with two different types of load. So first, we have the electronic load set up for a constant resistance or CR mode. And on the oscilloscope, we can see the output voltage is in blue, and now I have the output current in green. And you can see the output soft start waveform looks normal, and the output current functioning as a resistor follows the output voltage. So this is a common way to measure the output voltage soft start, but VPT's DC-DC converters will also start in a constant current mode. So we will switch the mode to constant current, or what's called CC mode. And we will turn the input on again, and we can see the output voltage waveform looks exactly the same, only this time the current came up immediately as soon as the output voltage came on, but did not affect the output waveform. Next, we can look at the output voltage with no load. So let's look at the output voltage waveform with no load. And we can see this time the output current stays at 0, but the output voltage waveform remains the same. So different load types in general do not affect the output turn-on characteristics of our DC-DC converters. In this video, we've covered various turn-on characteristics and waveforms of the DVHF 5-volt single converter, but these are applicable to all of VPT's isolated DC-DC converters. And one more tip for making these measurements, we always measure the input and output voltage directly at the converter pins to get the proper waveforms. Thank you.